My name is Omer. I'm a compiler developer at Mobileye, working on compilers for the Mobileye's IQ chip, which are used for autonomous driving capabilities. And today I will present a recently developed LLVM IR utility that I worked on, which we call Fallback, and it basically transforms load and store instruction into gather and scatter instruction in vectorized code in multiple scenarios. So first I'll begin with the motivation. Why is this utility even useful? I'll go on to present an overview of the utility and a usage example. And then I will present a cost model that each target can implement, so it uses the transformation in the most efficient way, and present some performance and robustness conclusions based on our experiments. So I'll focus on my lectures in architectures that employ hardware control loops with zero overhead. What that means is that the memory accesses in such architectures are pre-configured by the compiler based on compiler analysis. That way, during runtime, we don't have to compute the offsets of the load instructions because they are pre-compiled. We pre-analyze how memory accesses progress during the loop, and then we save the time during runtime. So these are in the load and store units. Now, such architectures usually also have scatter and gather units, meaning hardware units, because there are some cases where you cannot pre-configure the strides. The compiler is limited and can't compute it. So these have to be calculated at runtime. So as I mentioned, such architectures have limitations. So for once, there is a finite number of load and store units. So if a load unit is focusing on a certain memory access and its progression during the loop, so this load unit is taken. And also another challenge is indirect index accesses. So for example, as you can see here, that's an indirect access. The compiler cannot pre-configure its stride because the stride is actually dependent on another loaded value based on a user input. So in these cases, we would have to find another solution. So this brings us to the fallback utility. Basically, it's an LLVM IR transformation that converts memory accesses into sequential data, such as load and stores, in vectorized load and stores mainly, into indirect accesses, such as scatter gather. So just a reminder for those of you who are not familiar or forgot, so from the LLVM line graph, a load instruction in LLVM IR receives a single pointer to a vector or an element of data, while gather instruction receives a vector of pointers, each pointing to a specific element of data. This can be sparse data, it doesn't have to be sequential. So just remember that the load gets a single pointer, while gather receives a vector of pointers. So let's show a little example of how the utility is used. So basically, what we have here is a for loop with a store into an out buffer of a loaded value from base buffer, which the index for the base buffer is also a loaded value from the index array. So this is an indirect access. The compiler cannot pre-configure the stride on compile time. It needs to calculate it in runtime. So we would have to fall back the load, the read instruction from the base into a masked gather instruction. So how do we do that specifically in LLVM IR level? So the key to the transformation is manipulating the get element PTR instruction, which is the instruction that actually calculates the pointer that goes into the load or store or instruction. So how this works is we manipulate the get and transform it from a pointer to a single pointer to the sequential data into a vector of pointers to consecutive elements. I'm not going to get into every line of code here, but just look at the red marked indices. So the load instruction has a single pointer, while the gather instructions gets 4 pointers because it loads 4 elements, a vector of 4 elements. So how we do it in this example, we first multiply, we split the index into 4, which is the vector size, and then we add it to it a step vector. So we get 4 pointers, each pointing to one element of the original vector that was pointed by the load. And then with this vector of 4 pointers, we can use it as into a gather instruction. By the way, I didn't mention it, but the transformation from a store instruction into a scatter instruction is pretty similar, so I'll not present it specifically. Now, this was a rather trivial transformation. I just wanted to mention that there are far more complex fallback transformation like this that include pointer arithmetics that result in a chain of gap instruction, not just a single gap that needs to be manipulated, or all sorts of type reinterpretation. So I'll not get into it, but this is just to show that the transformation is not so trivial in every case. So now let's go into the cost model. How we can utilize our hardware resources with the fallback transformation. So let's assume we have a VLIW architecture, which is a very long instruction word. We want to perform all the instructions in the same like long instruction, and we have a limited hardware resource. We have 1 load unit, 1 store unit, and 1 unit for scatter gather in our hardware. So let's take a look at the example. We have a for loop again, but now we have 2 read operations, 1 from base 1 and 1 from base 2. So these are like, it looks like 2 loads, but again, we have only 1 load unit. So how do we do it? We need to convert one of the loads into a gather, as I mentioned before. But which one? Does it even make a difference? So we will need to decide, we'll need a cost model to decide which of the memory accesses are best to transform from a load into a gather. So let's see how we do it. So the targets may employ cost models that are architecture based, and those help to decide which memory access is best to fallback in order to maximize performance. So the cost model can have multiple factors. These are just some examples here. For example, the physical registers bandwidth, like maybe certain memory accesses are in a bandwidth that is preferred for the hardware. Indices calculation over time, which is actually what we are going to show in the example. Potential stalls, all of these factors and other factors that targets can employ go into the cost model that outputs a fallback decision, a single or more memory accesses that will be converted from a load into a gather or scatter. So if we take a look at our previous example, we see we have 2 loads, the one from base 1 and the one from base 2. So which one would we prefer to convert to gather? So in this case, we would prefer to lower base 1 into a gather because it requires less indices calculation. The load from base 1 is just from a single index that is like direct index, the induction variable of the loop, x. While from base 2, we will need, in order to get the exact offset, we will need to multiply x by 2 and then add 7. This would add a runtime calculation overhead. While if we load base 2 based on a compiler analysis with the load unit, we wouldn't have to do this calculation in runtime. So this is why we would prefer to load base 2 based on a pre-configuration in the compiler and gather base 1. This will maximize our performance, and we got this result through the cost model. So to conclude, I just want to present some performance and robustness conclusions from our experiments. So for starters, our compiler robustness has improved thanks to the fallback utility. We had some kernels that couldn't be compiled due to hardware limitations. But given the fallback utility that converts some of the load and store instructions, we managed to compile 5% more tests in our compiler. And it also helps developers that in the beginning try to write pretty naive code examples that are not fully optimized. So instead of getting an error like you exceeded the amount of hardware resources or stuff like that, they will just get a warning that the fallback has occurred, but they can still continue the compilation and verify their results, and only on a later stage they can optimize their code for performance. And even in some cases, we actually, the fallback helped improve performance results because it helped balancing unit pressure between load and store units and scattering other units. So that is it for me, and thank you, and let's get to lunch.